This video is for ELEC 1510 Logic Design. This is Lecture 19, Video 1 on State Reduction, corresponding to textbook section 5.7. We use state reduction to make the implementation of state machines as circuitry more efficient. Oftentimes, state diagrams can include redundant states that you don't even see in the state diagram. Two states are considered equivalent if they have the same next states and outputs. One of the states, that is one of the redundant states, can be replaced by the other in the entire state table. So we're going to see a few examples of doing this and making the implementation more efficient. So here's an example of a Moore machine that we're going to perform state reduction on. You can tell that it's a Moore machine because the outputs, the /0 or /1 is within the states themselves, meaning your output only depends on the state and not on the inputs. We have 6 states in this state diagram, A, B, C, D, E, F, and transitions between all of those states. It's difficult to tell just from the state diagram if this machine can be simplified or not. So we're going to do that using a process called state reduction. In this slide, we see the state table corresponding to the state diagram for the Moore machine that we're going to simplify. This state table looks slightly different than the state tables that we've used to design the actual circuitry so far. In this type of state table that we'll use for state reduction, you can see the current state, which is just listed as the letter A, B, C, D, E, F. We haven't yet assigned state variables or binary values to the states. In the next columns, you can see the next state based on whether the input is a 0 or a 1, and then finally in the last column, the output. Now what we can do is look at each row and see for the two inputs, x being 0 and 1, if the two next states for any given current state are the same and whether the output is the same. That will tell us whether there are redundant states in the state table or not. So let's start with the first row, A. A has next states A and F and output 0. If we go through the remaining rows, we'll see that there's no other current state that has next states A and F. So we know that A does not have a redundant state. Looking at B, we see that B has next states B and E and output 0. If we go through the remaining rows, we'll see that state F also has next states B and E and also has output 0, meaning F is a redundant state of B. What we can do then is simply erase state F from the state table, get rid of it altogether, and replace any incidence with F as B. Okay, so we've already simplified our state table somewhat. Now when we look at row C, C has next states A and D and output 1. And if we look at the remaining rows, we'll see that E has the same thing, next states A and D and output 1. That means that E is a redundant state of C. So we can go through and eliminate E. Anywhere that E appears in the state table, we replace with C. Now, the very last remaining row is D, which has next states D and C, and that doesn't match any other current state in the simplified table. So this is our new state table as simplified as it can get. We've been able to simplify our state machine down to only having 4 states, which means that we can implement it now with 2 flip-flops. The original 6 states would have taken 3 flip-flops, so this is a more efficient implementation. Let's now look at an example of state reduction using a Mealy machine where the outputs depend on both the current state and the inputs. So as you can see, the bubbles representing the states now only have the state number in them, so A, B, C, D, E, F. The outputs are specified for given inputs. So for example, there's an arrow above state A returning to state A, and it says 0/0. That means that for an input of 0, you give an output of 0. So when you're in state A and you receive 0 as the input, the output is 0. The state table that we're going to use for state reduction for the Mealy machine is given here. As you can see on the left, we have the current states A, B, C, D, E, F. We have the next states for input X being 0 and 1, and now we have outputs for X being 0 and 1 as well. So we repeat the same process for the Moore machine, but now we have to look for equality for the two input states as well. So for example, current state A has next states A and F, and the output is always a 0. If we go through the remaining rows, we see that there's no other case where the next states are A and F, so A has no redundant state. Looking at current state B, the next states are B and E. If we go through the remaining rows, we see that F has B and E, just like it did for the Moore machine, but the outputs now don't match. For B, the outputs are 0 and 1, and for F, they're 1 and 1. So F is no longer a redundant state of B. If we look at current state C, it has next states A and D and outputs 1 and 0, which matches row E. So E actually is a redundant state of C. So we can cross that off and replace any reference to state E in the state table with C. Now looking at current state D, it has next states D and C, which is not matched by any other row. Looking at state F, we now have B and C, which again matches B, but the outputs don't match. So this is as simplified as the state machine can get in the Mealy machine version. Unfortunately, we started off with 6 states and we're only able to reduce it to 5 states, which does not reduce the number of flip-flops. It still needs 3 flip-flops in order to be implemented, but hopefully now the functions that you would use to implement it would be a little bit simpler.